Okay, so let me just say it again. So A2, A1, A0 in the dark green come from a subset of the entire possible set of data. The entire possible set of data is the dark blue, these squiggles. I just meant to make dots there, but anyway, they didn't come out like dots. But they're the dark blue. The dark blue is the all possible data. And then we only have a subset, which was these blue blue dots here, this blue, this blue, this blue, and so on. And we say that those are not, that gives us a model, gives us this dark green line. That's a model, but we said the true model is the dark blue line because that fits the all possible data. And we can see that, the dark green model is not the same as the dark blue model. So these coefficients here that come from the dark green model or the light blue dots only estimate these. They're not exact. They only estimate it. So we'll say that the estimate of A2 is this A2. The estimate of this dark blue A2 is this A2. And the estimate of this dark blue A1, which we cannot know, like we said, we can't know it because we don't have all the data, is this. And the estimate of A0 is, the estimate of the dark blue A0 is the dark green A0. Okay? And so that's what this W with a hat there stands for. So we're just reminding ourselves that we're only working with estimates here. Like we can't know the true model. That's the idea. So I hope that's clear. Okay, let's go on. That the parameters are included here when we talk about this particular model, right? Once we have to choose a set of parameters to get a particular parabola. So anyway, we have this loss function, and so we already said that one loss function would be the RMSE, or we could use. Okay, so this is wrong actually. What I wrote here is wrong. So that this L here doesn't mean completely this. It's only part of this. So remember, what does the E stand for in RMSE?
Error.
The error. What does the S stand for?
Square.
Squaring. What does the M stand for?
Mean.
Mean. And what does R stand for?
Root.
Root, taking the square root. So once again, what does E stand for?
Error.
Error. What does S stand for?
Square.
Square. What does M stand for?
Mean.
Mean. And what does R stand for?
Root.
Root. Okay, good. So actually this thing is only the S and the E. So it doesn't have the R and the E, M. So if we want RMSE, we have to do the root mean of this. So this is just the SE. Yeah, right. It's just the S and the E. Okay, do you understand? So this doesn't mean the root mean squared error. This is just the squared error. And then if we want the root mean squared error, we have to take the mean of this and then take the square root of that. Okay, so that's what this notation means. I had it wrong. This doesn't include summing up and taking and then dividing by n. It's just the first part, just taking the squared error. And if we're using MAD, remember MAD is the absolute mean, what MAD means the mean absolute deviation. If we're using that, then this would be the AD part, not the mean. Okay, so that's the way she's using this notation in her slides. Okay, let's keep going. The MAD, so anyway, and we could. I said that here. Actually, in the video, in her video, the L function is defined differently. It's not the sum or the average. It's just the absolute value or the square of the area. So it's either SE or the AD. It's just the absolute value or the square of the area for a single point, not for all the points. If you want to do it for all the points, that means you're taking the mean. That's you have to take the mean of this. This is just for a single point. Think of other. When did that happen? MAD. And we could think of other ways to measure the loss. Okay, let's go on to her videos. One thing is that we might want to talk about first, though, is what's the difference between MAE or MAD? Actually, look, they're calling it MAE here, but we've called it MAD or MAE. So what's the difference between MAE here? What's the difference between MAE and RMSE? Okay, so that's an interesting question. I mean, they're not exactly the same thing. They might have some difference. They might have some consequence as to which one you choose. So what do they say is the difference here? They say the similarities are that they both express the average model prediction error, or they both the average error, right? Does everyone understand that? Of course. Okay, but what's the difference? So taking the square root of the average squared error has some interesting implications. So when we square the errors, what is that going to do? When you square errors, what happens? They get bigger or smaller?
Bigger.
Yeah, unless the errors are fractions, then they get smaller, actually. But if they're big errors to start with, they get much bigger, right?
Right.
So if you have, if you have some error, have we talked about the word outlier? In statistics, you should have learned the word outlier. So outlier, when you have some data, let's suppose I'm measuring this pen. I have this pen here, and I'm trying to figure out how much it weighs. So I'll put it on a scale, right? I'll put the scale here, and I'll put some weights over here, and I'll say, how much does it weigh? So one time I weigh it, and it says it weighs, 15 grams. And then I measure it again, and it says it weighs 15.1 grams. And I measure it again, and it says it weighs 15.11 grams. And then another time I get 14.98 grams. Okay, so I keep doing this, and I get more and more measurements. Then maybe what I'll do to say what the true measure of the of how much this weighs, I might take the average of all of these. That might be a good idea if I want to, because each time I measure it, I might get a slight difference. But if I take the average, maybe that's a good measure of what the true weight of this pen is. Now I get numbers like this, and maybe another number I get is 15.01 and 14.997 and so on. But then somewhere in here I get a number like 18. So all these numbers are super close to 15, and then I get something like 18. This would be called an outlier. So it's very far away from the rest of the data. Okay, that's called an outlier. Okay, so going back to here, if we get an outlier in our data and we're using so in other words, if we're talking about a model, well, so if we have a model and we have like that, and we have some points here, and these are all quite close, but suddenly we have one point up here, that's like a big outlier far away from the data or far away from the model. And if we do the RMSE of this and include this point, when this is an error. This is an error. So, but when we square it, it's going to be much bigger. So when you do RMSE, you square things that are really big, that's going to make the error look even worse. So if you have outliers in your data or whatever, then, and you use RMSE, this is going to be big. So this is very sensitive to outliers. That is, if you have big outliers, the RMSE is really going to say that your model is very bad. So if you have some big outliers as compared to the MAD might not give you such a bad report about your model, even if you have a big outlier. This is going to really blow up the outlier, and then it's going to say, oh, your error for this model is huge. It's really big, whereas this won't say the error for the model is so bad. So this one will respond to outliers and give you a bad report based on those outliers. So that's what they're saying here. So that's like a practical difference between using RMSE and MAD. So if you're really worried about outliers and you don't want a model which has big outliers, you might choose RMSE, because that will say, oh, that's a really bad model, so you won't use it in that case. Okay, so that's the idea. All right, let's go on now to her videos. So we're talking about this class that we talked about last week, Coursera, and it's this lady, her name is Emily Fox, and this course is, I forget what it's called. Let's see, what's it called? Machine Learning Regression, maybe, by University of Washington. And I'm looking at week 3, and we just covered the basics, so we don't need to go through these 2 videos, even though her discussion was 4 minutes and my discussion was 30 minutes. But anyway, let's go on to this. And I might stop and make comments here to explain.
So the first measure of error of our predictions that we can look at is something called training error. And we discussed this at a high level in the first course of the specialization.
Okay, now let me just ask you. We've done some data mining already. We used Weka. We worked with the iris data, and we had error, right? We talked about the error when we did the training, right? Everyone agrees, right?
Yes.
Yes,
Right.
Professor.
Right. Like, do you remember some error that we got? Any numbers? Do you remember any kind of numbers that we got? Anybody remember any numbers or approximate numbers?
Five over 14.
What would you say?
5 over 14.
Ah, 5 over 14. Yeah, we saw something like that. That's true. And how about like when we ran Weka? It gives you like a error, like overall, it gives you accuracy. Anybody remember any of those numbers?
Professor, I think we used J48 for, I can't remember which data set, but we got it like 67.28.
Right. Yeah, so we got, I remember something like 60%. That was the error. And I think that was for the weather data and J48
Yes.
or something like that, right? So
Yes.
we did this, right? We know about what we mean by the error, right?
Yes.
Now the question is, though, was Weka giving us, well, remember over on the left side of Weka, you have, what do they call it? The test options, I think? They call it the test options. And we had cross-validation was one choice, and another choice was percentage split. Do you remember that?
Yes.
Remember on Weka, you know, there's on the left side, here's Weka. On the left side, in the prediction panel, we had cross-validation and we had percentage split, right? Now let's think about the percentage split. Instead of cross-validation, a little bit more complicated, and it won't help us right now. So let's think about percentage split. So when we use percentage split, I think usually it's 66%, or the split is 66%. So when it gives us that result, maybe it said, like he said, maybe 60% or something like that was the accuracy. When it gives you that, is that in the test data or is that in the training data? When it measures how accurate it's performing, what its performance is it using the test data or the training data to measure the accuracy?
The test data.
The test data, right? Not the training data, right? Remember, what do? We use the training data to build the model, and then we take the model that we built and we apply it to the test data and see how well it does. Does everyone agree with that?
Yes,
Yes.
Professor.
So that's what she's talking about here. She's saying we don't want to test the model with the training data. And we don't do that in Weka. We didn't do that. We tested the model with the test data. And she's saying, that's right. We don't want to test the model with the training data. That doesn't make sense because the training data, the model is fit too closely to the training data. It's not really fair to use that to do the testing. We want to switch to new data to do the testing. So does everyone agree with that?
Yes.
Okay, so we don't want to test on the training data. That doesn't really make sense. And that's what she's going to be arguing here. So let's see that.
But now let's go through it in a little bit more detail. So to define training error, we first have to define training data. So training data, typically you have some data set, which are shown as these blue circles here, and we're going to choose our training data set.
Now, one more thing. In all of the problems that we've been dealing with in Weka, we were not using a numeric output variable. The class variable was not numeric. It was categorical. So this picture doesn't really make sense in that case. So you have to sort of realize, you know, that you can't exactly think of what we did before exactly when she's talking, because she's talking about using a numeric output variable. Price is the output variable. So it doesn't quite match with what we are doing when we're doing classification. The basic ideas we can use them in both cases, but the pictures don't look exactly the same. So just don't get too confused by that. So here, she's saying in this picture that we start out with blue, that's all of our data, but we're going to, I think she says the gray ones, I forget, either the gray ones are either the training or the test. Let's see what she says actually.
So training data, typically you have some data set, which are shown as these blue circles here, and we're going to choose our training data set to be just some subset of these points. So the gray circles are ones that are not included in the training set. The blue circles are the ones that we're keeping in this training set. And then we take our training data, and as we've discussed in previous modules of this course, we use it in order to fit our model, so to estimate our model parameters. And just as an example, for example, with this data set here.
Okay, so what kind of model is she going to try and fit here?
Quadratic.
Quadratic, which means what?
second degree polynomial.
Second degree polynomial, that's right. It's a polynomial second degree polynomial. So she's going to try and fit a quadratic or a parabola to this. And how is she going to do it? Well, this is called the sum of squares, and this means the root, the square root of the sum of the squares. That's the same thing we just talked about, actually. Isn't that like basically the same thing as RMSE? Okay, this is just another expression of the same thing. The sum of the squares of the error. Okay, that's what this means. The sum of the squares of the errors and then the square root. So it's really the same thing as the RMSE. But when you're fitting the model, sometimes they call it this. And when you're measuring the error, sometimes they call it the RMSE. So it's the same formula exactly, just a different name. Okay, so we need to fit the model. We're going to try and minimize the error. We're going to choose the green line, the green curve, which gives us the least error. That's what she means by this. So let's keep going.
Our model, so to estimate our model parameters. And just as an example, for example, with this data set here, maybe we choose to fit some quadratic function to the data. And like we've talked about, in order to fit this quadratic function, we're going to minimize the residual sum of squares on these training data points.
It's the same thing we were talking about.
So now we have our estimated model parameters, W hat, and we want to assess the training error of that estimated model. And the way we do that is first we need to define some loss function. So maybe we look at squared error, absolute error, or any one of.
Okay, so there's the loss function that we just talked about. Now it doesn't have, as I said, it's not summing up. This doesn't mean summing up yet. This is just the distance from the point to the, from the actual data to the model predicted value. And then do you want to take the absolute value of that or do you want to square it? That's all this part means here.
Of the many possibilities for our model. And the way we do that is first we need to define some loss function. So maybe we look at squared error, absolute error, or any one of the many possibilities for our loss function. And then the way training error is defined is simply as the average loss defined over the training points. So mathematically, what this is simply 1 over n, so n are the total number of observations in my training set, sum of the loss over each one of those training observations.
Okay, so we've talked about all of this now, right? This is the squared error. This stands for the squared error. And what's this W hat doing there again? What's the W hat doing there?
The estimated parameters.
Right, it's the estimated parameters. In other words, it's not the perfect model. It's only the model that came from our limited data, from our training data, which is very limited. So we put the hat on top, and we just remind ourselves it's W. It just means that we have some parameters. And then we sum this up and divide by n. And that's the training error, exactly what we said.
And just to remember, to be very clear, the estimated parameters were estimated on the training set. They were minimizing the residual sum of squares for these training points that we're looking at again in defining this training error. So we can go through this pictorially in the following example, where in this case we're specifically looking at using squared error as our loss function. And in this case, our training error is simply 1 over n times the sum of the difference between our actual house sales price and our predicted house sales price squared.
So this is just the whole equation that we just did. It's just the, this is the actual value minus the estimated value, and the actual value minus the estimated value. It's just this minus this, this minus this, this minus this. It's just all of that.
Where that sum is taken over all houses in our training data set. And what we see is that in this case, where we choose squared error as our loss function, then the form of training error is exactly 1 over n times our residual sum of squares. And I want to note here that there's some difference in convention that people use, whether there's the 1 over n as the definition of training error or not. So just be aware of that when you're computing training error and reporting these numbers. Here we're defining it as the average loss. More formally, we can write our training error as follows, and then we can define something that's commonly referred to just as RMSE, and the full name is root mean square error. And RMSE is simply the square root of our average loss on the training houses. So the square root of our training error. And the reason one might consider looking at root mean squared error is because the units in this case are just dollars, whereas when we thought about our training error, the units were dollars squared. Remember, we're taking the squares of all these differences in dollars, so the result is dollars squared.
For example, y1, let's use y1 and x1. So here's y1, the height of this point, and f of x1 is the height of this point. So let's say this house sold for $1 million, and this was $700,000 was the estimated price. So there's a difference of $300,000 here. So this number here would be $300,000, and then we're going to square that. So that's going to give us dollars squared. So that we don't really want an error that's in dollars squared. So that's another reason why we take the square root. So we're not working with dollars squared anymore.
So that's a little bit less intuitive as an error metric than just an error in terms of dollars themselves. Now that we've defined training error, we can look at how training error behaves as model complexity increases.
Okay, now this is where this is new, and this is interesting. What she's going to do is she's going to think about what happens to the training error when we consider different models that start out, models that are, first we'll look at very simple models, and then we'll look at more complicated models, and what happens to the training error. So can anybody tell me what's going to happen to the training error? In other words, is it going to get bigger or smaller as we use more and more complex models? So a very like a non-complex model would be a linear model, and a more complex model would be like a higher order polynomial, which allows the, to go up and down and up and down and so on. So which is going to have less error?
The more complex model.
Right. So that's what she's going to discover here. She's going to say, as we increase the complexity from, say, linear to higher order polynomials, as we keep going to the right, what's going to happen to the error? But she's going to point out that that's happening within the training data. So we have to remember that. We're doing this, we're thinking about this in the context of the training data. So anyway, let's see what she says.
So to start with, let's look at the simplest possible model you might fit, which is just...
So what's the simplest possible model?
The linear model.
Yeah, so you might say, oh, it's the linear one. But actually, there's even one simpler than the linear one. And that is, let's see. So let's go back to this, think about this just to make sure we agree that what the simplest model is. So like, here's a model, y equals, a8x8 plus a7x7. So that's a pretty complicated model, right? So we could go down, okay, we could do a7x7 plus a0. That's a little bit less complicated model. We could go down to parabola. That's a2x2 plus a1x1 plus a0. That's less complicated, less complex. And then we could go to this one, a1x plus a0. That's even less complicated, right? So this is going down in order of complexity, right? But there's one more that's even less complex than this one. What is it?
equals A0.
Right. And what does that look like? That's like saying y equals 5, right? What does that look like? That's a straight line, right? So that's the least complex model, right? Does everyone agree?
Yes.
Okay, so that's what she's saying. That's the least complex. So here it is. We fit a flat line to the data. That's the least complex model.
It's a constant model. So this is the simplest model we're going to consider, or could consider, and you see that there's pretty significant training error. So let's just say that that has some value here. This is the training error of the constant model.
And then as we increase
then let's say I fit a linear model. Well, a line. Model. These are all linear models we're looking at. It's linear regression, but just fitting a line to the data. And you see that my training error has gone down. So some other value that I'm showing with this pink circle here. Then I fit a quadratic function.
So this axis is the complexity, and this axis is the amount of error you get. So as the complexity moves to the right, we expect the error to decrease.
Again, training error goes down. And what I see is that as I increase my model complexity to maybe this higher order polynomial, I have very low training error, just this one pink bar here. So training error decreases quite significantly with model complexity. And
so here we have the simplest model on the left side, more complex model on the right, and the training and the error is going down. But remember, this is the training error. She's not talking about what would happen on the test data. This is just what would happen on the training data.
In total, now that we've gone through these examples, we can look at what the plot of training error versus model complexity tends to look like. So there's a decrease in training error as you increase your model complexity. And why is that? Well, it's pretty intuitive because the model was fit on the training points, and then I'm saying, well, how well does it fit it? As I increase the model complexity, I'm better and better able to fit my training data points. So then when I go to assess my training error with these high complexity models, I have very low training error. So a natural question is whether training error is a good measure of predictive performance. And what we're showing here.
Okay, so predictive performance, she means the performance in the test data. Okay, that's what she means by predictive performance. It means how well it performs in the real world, in the test data, in new data. Or they also call it generalization error, how well it works in the whole, if we had much bigger data set, not just limited to the training data. So is training error, the fact that some model does very well on the training set, does that mean it's going to do very well on the test set? What's your answer to that?
Not always.
Not always. Why? Because we are going to fit the model to this training data. We could fit it perfectly. If we use a high enough order polynomial, if we had 10 points here, I don't know how many blue dots she has, but if we had 10 points there, I think if we used a 10th order polynomial, we could match it exactly to the data. Maybe it has to be 11th, I forget. But I think 11th order. Anyway, if we use like an 11th order polynomial, we could match it perfectly to this data, this training data. That doesn't mean that it's going to work well on the test data, as you'll see.
Is one of our high complexity, high order polynomial models that had very low training error. So it really fit those training data points well. But how is it going to perform on some new house? So in particular, maybe we're looking at a house in this gray region, so with this range of square feet. Question is there something particularly wrong with having xt square feet? Because what our fitted function is saying is that I believe where I'm predicting that the values of houses with roughly xt square feet are less valuable than houses with fewer square feet.
Did everyone see that? This model says that if you have this square feet, the model says it's going to be worth less than a model that has this square feet. So is there some reason why having this amount of square feet is like not good for the price? It seems unlikely, right? It seems like the model is wrong, not that this is, there's some value of the size of the house which makes it worth less, even though it's a bigger house.
Because there's this dip down in this function. Do we really believe that this is a true dip in value, that these houses are just less desirable than houses with fewer or more square feet? Probably not. So what's going wrong here? The issue is the fact that training error is overly optimistic when we're going to assess predictive performance. And that's because these parameters, W hat, were fit on the training data.
So I mean, that was a lot of words she said, but she's just saying no. The training model, training error is not really such a good way to know about how it's going to work on the test data.
They were fit to minimize this training error, minimize residual sum of squares, which can often be related to training error. And then we're using training error to assess predictive performance. But that's going to be very, very optimistic, as this picture shows. So in general, having small training error does not imply having good predictive performance, unless your training data set is really representative of everything that you might see out there in the world.
Okay. Well, unfortunately, we couldn't go much beyond that, but we want to go and talk about the generalization error. That just means the test data error, basically. And we want to focus on that and see how complex the models should be in order to get the best result in the test data, in the generalization error. Okay, so that's what she's going to go on to discuss in this video and the next video. So there's a kind of interesting way to think about it, and we want to talk about that, and we'll continue later about this. Okay, any questions? So my video is up on YouTube. I guess I'll post a link to that. And then also her videos are there. So you can go back and review this. And so I hope to see people tonight at the seminar at 7:30. So please go there and pay attention. I think it will help your group performance if you can have a mentor. So you should get started with this seminar. Okay, anybody have any questions?
Excuse me, Professor.
Yes.
So about the second scrim.
Yes.
Our groups have a little bit questions about the derived variables.
Derived variables, yeah.
Yes. So basically, what kind of variables that we need to put in or improve for the analyze?
So I made a short video. I mean, I made a 30-minute video, right? Did you notice that?
Yes.
Okay. And also you have the textbook or the reading, right? One chapter about derived variables, right?
Yes.
Okay. So did you go through that reading?
Our group basically go through the video a little bit.
Okay. Well, the first thing you should do is go through the reading, or maybe, I don't know, first thing you do is go through the video, or the reading. And you should read it carefully, okay? And then if you still have, because it explains it very easily there, very simply, I think. So especially the beginning part is good, but the end part is even better. But you need to know the beginning part before you can do the end part. So you should read that though, because this idea of derived variables is very important. Like anybody can just throw something into Weka and get out, a model. But the using derived variables, that's kind of the creative part of data science. That's where you have to think about your data and what sort of combinations of variables might make more sense than just the original data that you have. The original variables, instead of taking the original variables, you want to combine them in some way. And they give examples of what they mean by combining them. So go through that and check what kinds of combinations might make sense. And then you have to think about your data and how you can combine variables or maybe transform variables to to represent things that are more important, quantities that are more important, and that could improve the performance a lot. And as I said, anybody can throw data into, Weka or RapidMiner or whatever, and just come out with a model. But that's not necessarily going to give you the best predictions. And one other thing is there's usually when you're doing data science, like you're like a data science expert, but you want to be able to work with, like suppose you're doing something in medicine. You may not be a medical expert, but you're a data science expert. You want to work with somebody who's in medicine, who's involved in medicine, and then together, that person is called the domain expert. That person is called, the expert in that domain, in that field, in the field of medicine in this case. So you want to work with a domain expert to help you, because they're going to have insight into the data that you don't have, okay? So, and they can sort of come up with derived variables that are important, or they can point to different, they can give you all kinds of perspective and information and pointers and tips and they tell you, oh no, that's not we don't want to do that, or something's wrong with doing that. So anyway, but we don't have domain expert, of course. But still, you can do some of that by thinking about the data. Right? Don't just blindly put it into Weka, but think about it and think about what combinations of variables might be important. By combinations, I mean like creating a new variable, which is the sum of two other variables, or creating a new variable, which is the ratio of two variables, or something like that, some combination of variables to create a new variable. Okay?
Okay, I see.
Okay, so that's what you're trying to do. Now, like for example, if you have the price of something and you have the number of items sold, right? If you have the price and the number of items sold. So one column, one variable is the price, and another column is the number of items sold. You might say, well, I think that I'm trying to predict something, and revenue will be an important predictor of that, right? You understand?
Yes.
So you might say, I should consider making a new variable, which is the price times the number of goods sold. That's revenue, right? Price times the number of things sold, like, $10 per item, and you sell 100 of them, the revenue is 10 times 100 is 1,000. So you might say, I should have another column, which is the revenue, because that's important for what I'm trying to predict. Right?
Yes, it makes sense.
Yeah. So you wouldn't do that. I mean, Weka doesn't do that for you, right? But that might be an important new variable to have in your data set. And, the only way you're going to know that is to think about it and think about what's important in what you're trying to predict and what new variables are, you can create that that represent something that might be important in helping you to make your prediction. And the other thing is like what they call normalizing a variable. So you start with variables that are, say, anywhere from 0 to 1,000, and then you can normalize them so that you sort of map them into the interval just 0 to 1. So from 0 to, so when something is between 0 and 1,000, if you get something really close to 1,000, then the new variable is going to be very close to 1. And when you have a variable that was between 0 and 1,000, and you have a value which is like close to 0, that new value is going to be close to 0. And something that was, okay. So anyway, that's called normalizing. So anyway, you should read that chapter because it gives you a lot of clear indications about making derived variables and transforming variables. And then you can look at my video also.
Okay, thank you, Professor.
Okay. Any other questions?
Excuse me, Professor, I have a question.
Yes.
Actually, for the second scrum, do we have to use both the data sets?
No, you only use one data set.
Okay, so just choose one of those and then do the analysis and stuff.
Right. So the first scrum was kind of to get you working, and I had you do 2 data sets, and then based on what you found, you might think one is easier or more interesting or better to work with. And now from now on, you're going to just use that data set.
Okay, Professor. Thank you, Professor.
Anybody else?
Professor?
Yeah.
Do we get any feedback from you about the 2 data sets that we chose?
Do you get any feedback from me about the 2 data sets? What?
For the first scrum, when we chose the 2 data sets, so do we get any feedback from you as of to which one to choose, or it's completely up to you?
No, it's up to you. It's up to you. You should do it based on what is interesting to you, what is, and what seems sort of like the better choice. Okay, so you should do that based on those 2 criteria. So what is more interesting, more fun for you, and what is the sort of, what's going to work out better as a data science project.
Thank you.
Anybody else?
Excuse me, Professor.
Yes.
Like, are we allowed to use other software to help us visualize like table out or this Scrum?
Yeah, you can use other, but I definitely want to see, like, okay. Yeah, you can certainly use others because others tend to look better. But I hate to say this, but for every picture you make with another software, you should make a similar type in Weka. I mean, if it's possible. I'm sorry, if it's possible. If not, if you make a type of picture that you can't generate in Weka, then you can still use the one from another software. But I want you to also use Weka. I want you to learn how to do all of the things that we need to learn how to do in Weka. So I want you to use Weka. Okay, but you can also add to the project with other software as well. Okay, but I don't want you to skimp on Weka. Okay, that makes sense?
Thank you, Professor.
Okay. Any other questions?